In Nagari, Kasang, West Sumatra, when the river rises, so does the morbidity curve, an environmental health risk assessment of flood-disrupted communities. Only 21% of residents have formal water service. Most rely on shallow wells less than 10 meters from septic tanks. When floods hit, source water shows E. coli at 240 per 100 millites against a standard of 0. Across 4 disaster phases, clinic data tells the story. During peak flooding, diarrhea surged 79%. Infectious gastroenteritis and coptit emerged entirely new. This is infrastructure failure written in disease data. Here is the critical finding. Every pollutant individually passes its standard, but sulfur dioxide, nitrogen dioxide, and PM2.5 all target the respiratory system combined. Their hazard index reaches 1.90, nearly double the safe threshold of 1.0. 4 targeted engineering interventions break the transmission chain. Rainwater harvesting bypass contaminated water. A waste facility removes fly vectors. Drainage upgrades cut stagnant water. And a green belt filters particulate matter. Disease response to cumulative exposure and system failure, not isolated parameters. Infrastructure as barrier. That is the engineering contribution.
Welcome to the breakdown of an integrated environmental infrastructure design. We're looking at a Capstone project centered on Nagari, Kasang. The primary objective here is to engineer strict infrastructural solutions that build flood resilience directly into an industrial buffer zone. To understand the challenge, the engineering team first had to look underground, specifically at the dominant local soil types. The ground here is mostly troposalmons and a gravel sand mixture known as Sirtu. Their defining characteristic is incredibly high permeability. When seasonal flooding hits, this porous earth acts like a sieve. It allows for the rapid, unfiltered subsurface transport of water across the entire area. Above ground, the demographic reality complicates things. Between 95 and 98% of homes here rely on basic, unsealed on-site septic systems. Combine those unsealed septic tanks with highly permeable soils, and you have a severe structural vulnerability. Any major hydrometeorological event instantly creates a massive risk for subsurface contamination. Field surveys of the area revealed a specific, severe proximity hazard. This diagram details the proximity hazard. Septic tanks sit less than 10 meters from shallow drinking wells. In impermeable soil, this creates a direct underground pathway for pathogens. Tests recorded E. coli at 240 mpn per 100 milliliters, obliterating the government mandate of 0. This biological contamination has a direct line to local epidemiological morbidity records. This chart correlates health records and rainfall, confirming a 79.07% surge in diarrheal disease cases precisely during flood disaster periods. This epidemiological spike proves the on-site sanitation architecture has completely failed. To stop the pathogen cycle, a centralized engineering intervention is required. To translate these real-world field failures into viable infrastructural solutions, the team needed a rigorous methodology. This flowchart maps the data-to-design pipeline framework. It begins with primary data acquisition, pulling together household field surveys, direct topographic measurements, and water quality sampling. That data then moves into analytical methods, where a critical step is hydrological return period modeling. The engineers selected strict criteria for this, applying a 10-year return period metric for secondary networks and a 25-year metric for the primary drainage channels. Adhering to those strict return period models establishes a non-negotiable zero inundation standard. Achieving that baseline is a prerequisite before any new wastewater or clean water facilities can be safely designed. The primary wastewater intervention removes the individual permeable on-site tanks entirely, replacing them with a centralized closed-loop network. This map displays the macro-level layout of the proposed communal pipeline network across Nagari, Kasang. You can see in the system architecture details how this network definitively routes both gray water and black water away from highly permeable residential soil zones. The wastewater enters a central treatment plant through 5 stages. The screening chamber filters solids, passing to a settler for sludge. The anaerobic baffled reactor degrades organics. The aerobic biofilter uses a honeycomb structure for secondary reduction. Finally, a chlorinator neutralizes pathogens before safe discharge. Translating that specific blueprint into reality requires strict capital allocation. The project outlines an allocation of 4.96 billion rupiah, dedicated strictly to excavation costs and the heavy-duty conveyance materials needed for the pipe network. An additional 3.58 billion rupiah is required for constructing the core processing facility itself. Implementing this closed-loop, multi-stage pipeline design definitively severs the hazardous fecal-oral pathway that plagued the community's baseline data. With sanitation secured, the team engineered a secondary infrastructural intervention focused entirely on safe drinking water. The objective here is a decentralized rainwater harvesting system. It provides an emergency water supply that bypasses both the highly turbid municipal networks and the contaminated local wells entirely. The system is designed against a specific demographic load, serving 180 individuals across the 45 most severely affected households. To meet that demand, the system targets a strict operational capacity of 2,700 liters per day. This blueprint details the rainwater harvesting setup. Roof runoff enters PVC gutters. A first flush diverts the initial wave, isolating industrial dust. Water passes through a slow sand filtration unit, reducing turbidity, finally entering dual HDPE tanks, where it's disinfected via a floating chlorinator. By integrating those first flush and filtration technologies, the design creates an autonomous, high-quality water reserve specifically engineered to withstand the area's heavy industrial atmospheric fallout. Moving from individual blueprints to macro-level feasibility requires strict project management. This Gantt chart plots the formal implementation schedule included in the detailed engineering design, mapping the exact phases of procurement, excavation, and construction. This vulnerability versus resilience table directly compares the engineered future state against the previous baseline conditions. Under sanitation architecture, the region shifts from unregulated, highly permeable septic tanks to a fully sealed, high-durability wastewater treatment network. For water security, the system moves past systemic municipal failures during floods to an autonomous harvesting system guaranteeing 2,700 liters per day. Looking at pollutant exposure, the direct ingestion of industrial dust is neutralized by the automated first flush and slow sand filtration pairing. But perhaps the most critical metric derived from this engineering overhaul is the economic impact. The model projects a financial return of 2 billion rupiah per year saved in reduced medical prescriptions and emergency environmental cleanup costs. By processing exact geological vulnerabilities and local precipitation data, the team successfully formulated stringent, fully compliant infrastructure designs. This integrated master plan establishes a viable, replicable framework for neutralizing hydrometeorological hazards in some of the most vulnerable industrial buffer zones.
Nagari Kasang is an area where industrial activities, transportation corridors, and residential settlements are located in close proximity. This project was conducted to assess existing air quality conditions and develop a preventive mitigation strategy. Ambient air quality monitoring showed that total suspended particulates, PM10, PM2.5, carbon monoxide, and non-methane hydrocarbons all remained below applicable environmental standards. However, industrial stack emissions, transportation activities, and road dust were identified as potential sources of air pollution. Wind pattern analysis indicated dominant winds from the east and west, suggesting that pollutants may be transported toward nearby residential areas. These residential settlements were therefore identified as the primary sensitive receptors within the study area. Based on source locations, wind patterns, and receptor distribution, a greenbelt system was developed consisting of 3 components. The industrial buffer greenbelt provides protection along the industrial boundary. The green corridor enhancement strengthens ecological connectivity and supplementary pollutant interception. The residential roadside greenbelt helps reduce roadside dust exposure for nearby communities. The proposed system has a total length of approximately 2.2 kilometers, with an estimated implementation cost of 329 million Indonesian rupiah and an implementation period of 7 months. In conclusion, although current air quality conditions comply with environmental standards, the proposed Greenbelt system provides a practical long-term strategy for protecting surrounding communities and supporting sustainable.
Here is the layout for the TPS-3 Nagari Kasang Waste Management Facility. The building measures 48 by 36 meters and covers a total area of 223 square meters. The structure incorporates a metal roof and 1.5-meter half walls for secure ventilation. The floor plan separates operations into 9 distinct zones. When your collection vehicles enter the main gate, you route materials based on the waste type. You direct organic waste to the receiving area. Next, you shred the material and move it into the rotary kilns for composting. Workers then screen and package the final compost product. You process recyclable materials using the press machine. You must store all leftover non-recyclable materials in the residual waste bin. The facility includes an administration office, worker restrooms, and a parking zone for your collection vehicles. The internal circulation path allows your vehicles and personnel to navigate safely through the site.